to it inside of the structure. But henceforth, thanks to the type def, we can just call this thing a node. So that's how we might actually implement that in code. But let's actually now use this same idea, these pointers and these linked lists, so to speak, and those concepts from Monday to start making more interesting structures. So this is what in computer science is generally known as a tree. It's kind of like a family tree where there's one patriarch or matriarch at the very top of the tree, and then you have all of the descendants beneath it. Well, what do these nodes each represent? Well, let's just toss some jargon out, and we'll actually see this same jargon with HTML next week. So anything at the top here that has arrows emanating from it but not into it is going to be called the root node. So that's, again, the sort of oldest person in the family at the top of the tree. 2 and 3 here we would generally say are children of node number 1. 4, 5, 6, 7 are grandchildren of node number 1, but in turn children of 2 and 3. And these things down here like 8 and 9 and even 5, 6, 7, since we already have this tree analogy, well, this is going to be leaves of the tree. Anything that has arrows coming into it but not actually leaving it. So these arrows at this point in the story just represent pointers. So if you want to create some kind of tree structure, you can actually use pointers to chain them together. So once you do this and have this ability to chain nodes together, we can actually start solving some problems in more sophisticated ways. And again, the goal here of this week and 2 weeks ago in introducing these data structures is to not have to fall back on simple variables and simple arrays. We can now start building and wiring things together in memory. So this, I claim, is a binary search tree. It is conceptually identical to the notion of a tree that we just slapped some jargon on. But there's some key feature of this binary search tree. If you look at its numbers, what pattern do you see, if any? What's that? Yeah, the leftmost is the smallest, and conversely, the rightmost is the biggest. It's actually a coincidence that they're all double digits here, or identical digits. But notice that on the left are small numbers, on the right are small numbers. But more specifically, if you look at any specific node, its left child, so to speak, is less than it, and its right child is greater than it. And with that recursive definition, we can infer that all of the nodes in this tree are indeed in sorted order from, so to speak, left to right. There's 22, and that's a child of 33, so 33 is indeed bigger than it. But 44 is the right child of 33, so he's bigger than 33. But 44 is smaller than 55 because he is a left child descendant of 55. Right? So anytime you go left, everything to the left of 55 will be smaller. Anything to the right of 55 will be greater. And that same definition can be applied recursively, so to speak, to 33 and 77. So who cares? Why is this useful? Well, thus far, we've been only using arrays. But suppose that back in the day when we had all those pieces of paper on the board, we instead transformed that array into a tree structure where we had a pointer pointing at nodes that were arranged in this way. Or just imagine students, for instance, standing awkwardly with these numbers but pointing at each other with multiple hands this time. What's the running time of doing search on a data structure that's called a binary search tree? How many steps does it take if there's n nodes or n numbers in this tree? So it's actually log n. And what's nice here is that you can actually see this. Even if you're still a little rusty on logarithms, logarithms in this class have generally involved dividing something by 2, dividing something by 2, again and again and again and again, dividing and conquering. Well, what are you doing in a picture like this? Well, if you take n nodes and you have one at the top, but then each node has 2 children, 2 children, 2 children, that's effectively the same as having the total height of this tree. So in other words, what's the height of this tree if you actually have 1, 2, 3, 4, 5, 6, 7 total nodes, which is roughly 8 total nodes, give or take, if I just have an off by 1 error? Well, it's actually log base 2 of 8, or 3. So the height of this tree is 3, which means if I want to find like the number 44 and I start at the root of this tree, which just like a linked list, you start at one special pointer. In the context of a tree, you start at the top, the root. How do I find 44? Well, I first check, is 44 less than or greater than 55? If it's less than, I go this way. But notice conceptually, just like our phone book, that has the effect now of snipping off this entire branch of the tree, so I don't even need to go there anymore. So even though it's not quite perfect division, the problem has just gotten halved. give or take, in size, because I now only consider the left branch. So now I'm at 33. Is 44 less than or greater than 33? It's obviously greater than. So now I chop off this branch of the tree. Not as exciting because it's a tiny little leaf, but if you imagine now a much, much bigger picture, you're really pruning the size of this problem, and huge branches, huge halves of the problem are falling off with every descent into the tree. So how deep might 44 be? Log base 2 of n is the answer, or just generally log n. So anytime you have a tree structure, you have this opportunity to really improve the performance of inserting things or finding things or even deleting things. And in fact, you've probably at least heard the term database before. We'll use a database called MySQL toward the end of the semester. And one of the key features of databases these days is to let you insert and delete and retrieve data really fast. And they typically do this using tree structures like this. Databases actually use something called a B tree, which is a little more sophisticated, but this idea is the same. You might have some node in memory pointing to some other nodes, to some other nodes, to some other nodes. So these data structures might get kind of wide, which is OK. They don't get very tall, because it's in the height that you end up wasting time searching deeper and deeper and deeper. So how do we implement this? So now it should be getting a little easier, right? Given a picture, you can kind of translate it directly to C code. Here's a new definition of a node. So I'm using the same word, node. But inside of this node is going to be an int n for 55, 44, 33, and so forth. And then each of these nodes needs a left pointer and a right pointer. And just to follow the logic, what is going to be the value of the left pointer and the right pointer for any leaf in a tree? Just null, right? We already have a special value to represent that. So we can literally build this kind of structure, more sophisticated though it might be than anything we've done before, using just these basic primitives, an int and a couple of pointers. So let's continue this idea. Rather than have each of our nodes be a little tiny circle with just an int, what if I cram an entire array of pointers into a node? So this is what's called a trie, T-R-I-E. The name apparently derives from retrieval, even though people say try, so retrieval. But it's a trie, and that's a play on words. It's a tree, but it's used for retrieval. That's the quick, completely mangled history of tries. So a trie is a data structure, though, ultimately that looks like this. Each of its nodes is actually an array, and typically each of its arrays represents a letter of the alphabet. And that's an oversimplification because sometimes you need to deal with punctuation and whatnot. But a very common approach to implementing a dictionary for something like a website or a spell checker is to use this trie data structure, whereby each node, again, has an array of pointers, so that if you have a word like Alice, how do you store Alice into a trie? Well, you start at the so-called root, which is the rectangle at the very top of the picture. You index into the leftmost element of the array for A. Then that brings you to a new node. Then you index into the L location, then the I location, then the C location, then the E location. And you sort of implicitly store Alice in the tree by sort of marking the spot at the end of this path you're taking from top to bottom in the trie, saying Alice was here, so to speak. And now this picture has done it for what words? Well, we have Turing on the right. So if we start with the letter T, U, R, I, N, G, all the way over there on the right. Now realize this picture, it would be impossible to read if you drew all of the arrays, so that's why they've chopped them off. So this refers to Alan Turing, a very famous computer scientist, the so-called father of computer scientists. Also take CS121 for more information. Who's all the way on the left? We have Maxwell. So Maxwell's equation, M-A-X-W-E-L-L. And what's with these triangles? This is just arbitrary symbology here. What does that probably represent? Yeah, null of some sort, or it's this sort of like conceptual check mark, like Maxwell was here and Turing was here. And so that we have to somehow remember that a name stops here. So the goal here is to insert a whole bunch of names, or more generally in a dictionary, 150,000 words into a data structure. And what's curious here is that we don't actually store the names. Instead, we implicitly store the names by way of these pointers. Because again, you have 26 pointers, or maybe 27 or more if you have apostrophes or other punctuation that appears in names. You kind of walk through this tree, allocating these nodes as soon as you need them, and then just check off at the bottom, or with this delta symbol, someone was here. So you implicitly store among all these pointers some kind of identifier. So what's really powerful here? What's the running time of looking up someone in this data structure if the name is Maxwell? Well, how many steps does it take to answer the question, is Maxwell in this data structure? If you start at the top, you go M, A, X, W, E, L, L, and maybe one more just to get to that special sentinel value. So 8 steps. Now contrast this with one of our earlier designs, which was actually pretty fancy at the time, a hash table with separate chaining. How many steps might it take here? Well, it might actually take big O of n over k, because again, doesn't matter how big or small Maxwell's name is here. The running time of a hash table seems more dependent on the number of other words in the data structure. Right? Because if there's lots of Alices and Bobs, the chain might be long. But in the case of a trie, what's kind of neat is that by construction, no one is in Maxwell's way as you kind of weave your way through the tree. So the running time of a trie for looking up a name, and I need to come up with an arbitrary new letter. Let's just call it M, big O of M. But what does M represent? The length of the word, the name. And here's what's kind of neat asymptotically. If you assume that there's a finite limit on the length of people's names, or just words in the English dictionary, and that really is the case. You can search through the whole dictionary and figure out that the biggest word is of this many characters, 48 characters, or something crazy, crazy large. Well, technically then M is a constant. So if it's a constant, we throw away constants, which means big O of M is equivalent to big O of 1, and here we have it, this holy grail of data structures, right? We can now look up words that are of some length, but bounded length, in effectively constant time. And heck, even if it's not constant time, it's like MAXWELL plus 1, so like 8 steps to find a letter. Whereas before, if I had 1,000,000 words in my dictionary, or 150,000 words in my dictionary, I could maybe divide that by k, 26. I'm guessing that's going to be more steps than just 8. As in this case. Now, this is not necessarily, unfortunately, there's always a catch, the direction you want to go in when implementing the fastest possible spell checker, for instance, because what are you paying to get this seemingly amazing performance? What's this feature costing you? Memory, right? Yeah, this picture is kind of misleading in that they only show the letters, or really the pointers that you're actually using. But what's not shown in this picture? For every one of those nodes, it's currently not showing the 25 other pointers that represent the other 25 letters of the alphabet that you're just wasting, right? There's absolutely words that just don't exist. So you might not have a word like A, B, B, C, Q, 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 like random sequences of letters that technically you could follow pointers through the picture, because those might be prefixes of other words, but there's no little check mark at the bottom. There's no triangle. And yet you have to spend that memory if you're using arrays. Well, OK, well, arrays, our solution to arrays is always, well, if you're wasting space with an array, use what data structure instead? Like a linked list. So in each of these nodes, wait a minute, let's not waste 26 or more pointers for every letter. Let's just use one node per letter. But the problem with linked lists is that you give up random access. You can't just jump to the letter A, the letter B, the letter C. If you devolve it back into a linked list, now you have to search. So then the process becomes not so much going from top to bottom like this, as in the case of Maxwell. You instead have to kind of go left to right, then down, left to right, down, left to right. So you have a lot of lateral searching, which is going to cost you time, but save you space. And it turns out in terms of implementation, hash tables can, in fact, even though theoretically and asymptotically they're much slower than constant time, in reality, because tries use so much memory, they can actually perform much more slowly. But really, for PSET 6 every year with the fastest spell checker possible, you typically end up choosing between one of these two data structures, hash table with chaining or trie, and then deciding whether or not it was a good decision or how you can improve upon it. So in a trie, how might we represent this notion of a check mark or that little triangle? Well, let's just call it a bool, right? It's an is word. Yes or no, Maxwell was here or Turing was here. If it's false, there's no word that stops here. If it's true, there was a word. And then here, struct node children. Well, notice I'm borrowing the lexicon of like a family tree where a node has a bunch of children, each of which is a pointer to another node. But 27 of them, why 27? Well, in this case, as you'll see in this particular pset, we allow for alphabetical characters and then also apostrophes, which are actually pretty common in English words. But we disallow other crazy punctuation that does exist in some words, but isn't necessarily common. So we can solve, though,